Welcome. This lecture is about feature importance. Today, we want to understand the motivation for feature importance, develop an intuition for possible use cases, and know the characteristics of different feature importance methods. So remember that feature effects describe the relationship of features X with the prediction Y hat. This gives us one plot per feature, but it does not take the true target Y into account. On the other hand, feature importance methods quantify the relevance of features with respect to prediction performance. This condenses to one number per feature, and it also provides insights into the relationship with the true target Y. Note that here, when we talk about feature importance, we mean loss-based feature importance, but there are also variance-based methods, or a few methods on Shapley values, for example, which we don't cover here. Let's start with an example. Remember the bike sharing data, and on the right, we see feature effects plots for the bike sharing data. This gives us quite a comprehensive picture. So you see PDP and ice curves of categorical features, a lot of box plots. But it's also quite some information to comprehend. On the other hand, here on the left, for feature importance, you just get a single number per feature. So for example, for the temperature, you get the single number of a feature importance of about 4. We'll see in more detail what exactly that means. You can also do repetitions and by that estimate a standard error. But in the end, this gives you in one plot, one number per feature, a very easy to access information on the importance of the different features of a model. We'll see that different loss-based feature importance methods are based on common concepts or schemes. The first is perturbation or removal, and that means that we generate predictions for which the feature of interest has been perturbed or removed. And then the second step in the performance comparison, compare the performance under the perturbation or removal with the original model performance. And we will see that depending on the type of perturbation or removal, these different methods might provide different insights into different aspects of the model or the data. So in more detail, we'll talk about 3 different interpretation goals. So the first one is the feature xj causal for the prediction? The second is the feature contain prediction relevant information about y, so the true target. Or 3, does the model require access to xj to achieve its prediction performance? So let's start with the first one. So that means causal for the prediction means that if we change the feature value xj, that has an effect on the prediction y hat. So for example, in a linear model, this will always happen for a non-zero coefficient. Or in machine learning methods, that there is some kind of feature effect present. So for example, in tree-based methods, you might have a split on that feature, or a neural network, you might have non-zero weights. But note that this is causal for the prediction and not causal for the ground truth. So you cannot infer causal effects from methods that provide information about if a feature is causal for the prediction. So as an example, consider disease symptoms, which a model might use to predict the disease status. So you might be coughing and use this information to predict your COVID disease status. That means causal for the prediction y hat. But intervening on a disease symptom does not have an effect on the disease. So that means that it's not causal for the ground truth y. So if you stop your coughing, that doesn't mean that you're not COVID positive anymore. So that's a very important distinction if we talk here about causal. So to give an example, here we might start with overfitting. So for example, noise here does not have an effect on COVID risk, obviously, because it's just noise data, just generated noise. So there's no effect. But the model might include an effect of noise just because of overfitting. Or it might also happen, that is our example from the slide before, that you see that in the real world, COVID has an effect on your test result. So if you have COVID, your test will be positive. But in your model, that error is in the other direction because the model uses the test result to predict the disease. So this can be very different in the real world and in your model. And you have to be careful on using your model information to make claims about the real world, as the symptom example shows. So the second goal is, does the feature xj contain prediction relevant information about y? So now this is y. So the ground truth or true target and not the prediction. It's a different to the first goal. And the question here is, does the feature of interest predict the target with respect to the performance? And if xj is independent of y, then the two have zero mutual information. And that also means that the conditional expectation here is the same as without using the feature of interest. And that means that xj has no prediction relevant information. So for an example, we might here look at underfitting. So for example, here on the left, we see that the number of contacts has an effect on the COVID risk, but you see in the model that the number of contacts here is not detected as having an effect on COVID risk. So this is classical underfitting. The third goal is about, does the model require access to the feature of interest to achieve its prediction performance? So now it's not about the prediction and not about the true target, but it's about the prediction performance. So does the feature xj help to predict the target with respect to performance compared to using only x minus j? So here we mean by xj the feature of interest, and x minus j is all features except the feature of interest. So here, if the feature of interest is independent of the true target conditioning on all other features, then the expectation, the conditional expectation on x minus j is the same as the conditional expectation on xj and x minus j. And this means that xj does not contribute any unique prediction relevant information about y. So it might just happen that you have several correlated features in your data. And in this example, a random forest might, if you see here, the expectation is not the same. So the random forest relied on x1 to predict, but it might also be that x2 contains the same information. So if you condition on x1 and x2, this is the same conditional expectation than just with x1. So to give an example, you first might look at correlated features. So trust and vaccinated are correlated in the way that with increased trust, you have a higher vaccination rate. And that has an effect on COVID risk, but there's no direct effect of trust on COVID risk. And here it might be that trust has prediction relevant information, but the model does not need access to trust for the prediction performance because it's enough if the model has access to the vaccination status. So here, another example would be classical confounding, where you might be interested, to give the very classical example, you might be interested in the effect of smoking on the rate of heart attacks. And now it might look like that you have information on people drinking alcohol and if they smoke or not, that alcohol has a causal effect on heart attack rate, and smoking is in whatever way correlated to alcohol, but there's no direct effect of smoking to heart attack. And now you have to be careful to always consider alcohol in models when you want to estimate the effect of smoking on the heart attack. And this is the classical confounding example, where it's not the same of having prediction relevant information, because smoking does have prediction relevant information, but the model also doesn't need access to smoking to make its prediction, because the true cause here would be alcohol. Obviously, this is a made up example.